So first, I guess we'll finish up our discussion of second-order systems, dynamics of second-order systems, actually by going back to some circuits. Can you go down to the pad? And we'll look at two sort of classical circuits that are simple, but actually come up in a lot of applications. And they'll be good examples of second-order systems. There's really not, there's actually nothing more to say about second-order systems. You now know basically everything there is to know about them. So this is more an exercise of giving you an example and then actually getting an intuitive feel for what these things mean. Up till now, it's been just a quadratic equation. And if the roots are real, it means one thing. And if they're complex, it means something else. And growing, decaying, decay rate. This will help sort of give you a good intuitive picture for why it makes sense. So here's a parallel RLC circuit. If I take R equals infinity like this circuit here is an oscillator, right? There's no mechanism for damping. What this circuit does is it simply oscillates. Unless the initial conditions are 0. If they're non-zero, this oscillates. And what happens is very, very simple, and you can even sort of get a good intuitive feel for it. And let me just describe that. I'll take 30 seconds and describe why it is that this circuit here, oscillates. Let's imagine for fun that that the initial condition is no voltage and 1 amp of current in the inductor. Okay? So that's what it looks like at t equals 0, and let's let the thing go. So there's an amp of current flowing into this capacitor. What happens to the capacitor? What does the voltage here do? What? It increases. In fact, at what rate? Let's make this 1, 1, and there's a current of 1 ampere flowing in. 1 volt per sec, exactly. So the voltage across this capacitor is 0 and starts growing at 1 volt per sec. Okay? Well, this voltage, right, is actually going to, what's it going to do to this current here? Eventually. It reduces the rate of change of the current, right? So in fact, the current slows down. And in fact, eventually, we'll find out, well, we can calculate exactly when that is, but eventually, you know the solution is a sinusoid. When you get up to the very top of that bump, what happens is the voltage here is now at its maximum value and the current is 0. If I were to open a switch right then, everything would just stay just the way it was. Everything would be happy. What's happened actually from an energy point of view is that when this thing started, there was no voltage here, there was no energy stored in the electric field, all the energy was stored in the magnetic field. So in this quarter cycle of the sine wave, what's happened is the magnetic field has collapsed completely, and all of the energy stored in that magnetic field has been transferred to the electric field of the capacitor. Anyway, now the whole thing repeats and the energy sloshes back and forth. So this is the intuition. Now when I put a resistor here, it's probably, what I want to do is I want to talk about it intuitively before we actually start writing equations. When I put a resistor here, what happens is every time there's a voltage across here, what does this resistor do? Whenever there's a voltage across the circuit, what does a resistor do? It takes current, and what does it actually do with the current? What does the energy do? It dissipates. It heats up the resistor. Okay? So a good guess is that if R is really, really large, which is an approximation of that, which is when R is infinity, a really good guess, not a bad guess, is that if R is really, really large, this resistor will sort of take a little bit of energy each cycle. That's kind of the idea. And so what will happen is we're going to get a damped sinusoid. This is just intuition. Okay? What if I make R exceedingly small, really small? What happens here? Yeah, what happens is all the initial current here flows through here. In fact, you hardly ever get any voltage buildup across here. The capacitor is almost irrelevant. And what happens is you have an LR circuit, and it simply, all the energy stored in the magnetic field comes out as heat. Okay? Okay, so that's the idea. Let's write down the circuit. When you write down the circuit equations, you get this equation here. That's a classic second-order differential equation. And the first thing to notice is that if your resistor, capacitor, and inductor are all positive, then it's stable. Okay? So, and people, you can sort of laugh and say, oh, come on, everybody knows resistors, capacitors, and inductors are are positive, right? Which is true once you find sort of lying around. In fact, using an active circuit, you can actually make a negative inductance, a negative resistance, for example, in which case the solution of this could, for example, oscillate or grow. And in fact, that's a common form of an active oscillator, is to actually is a so-called negative resistance oscillator. Okay. Well, now now you know whenever you see a second order differential equation, everything depends on the roots of this polynomial, s squared plus s 1 over rc plus 1 over lc. You look at the roots of that, and that's going to determine the nature of the solution. Okay? Are the roots real, for example? We already know both roots are negative, right? That's what it means to be stable. Both roots are negative, or always have negative real part. Now we just look and see. The critical thing is is critical damping. Are we above or below critical damping here? Well, that turns out to be, in general, well, here it's just b squared less than 4ac. You work out what that means, and it says r is less than square root lc over 2. That's, so critical damping is r equals square root lc over 2. If r is less than that, it's overdamped. And if r is bigger than this number, then it is underdamped. So in other words, if r is bigger than square root lc over 2, this circuit, the solutions are damped and sinusoidal. Okay? If r is really, really big, I mean, if r is infinity, the solutions are precisely sinusoidal. If r is really, really big, and now we can be quantitative. Really, really big means really, really big compared to square root lc over 2. If r is really, really big compared to square root lc over 2, then the solutions of this circuit decay very slowly. And this matches the intuition, which is that basically it's an oscillator, like this, with a resistor there that turns a little bit of energy into heat each cycle. And then this is why you have a slowly decaying sinusoid. As you decrease your resistor, as you decrease your resistor, you start dissipating more and more energy. And when you get to a critical point, that's r equals square root lc over 2, here's what happens. At that point, the solution here is no longer sinusoidal. In other words, it kind of looks like this bump that you saw. It's this te to the minus t type solution. For r smaller than that, the dynamics of this circuit are given qualitative. It's a sum of two decaying exponentials, okay? Which is very interesting because it basically says that, I mean, if you, I guess to put this back in 101, in 101 land, you would do this, or you might do this. That's an LR circuit. Did you study this in 101 or not? Maybe. Okay, so and so I could come up to you and I could say, what's that? And you would certainly say, oh, I know exactly what that is. And I could ask you, what's the dynamic? What does it do? And you'd say, well, the current decays exponentially. And I could say, well, explain it. And you'd say, well, there's a magnetic field in here, and the magnetic field, the current can't go to zero immediately, and all the current here is, heats up the resistor, and all the magnetic energy gets turned into heat, or something like that. Okay, fine. And then I could say, this I know you studied in 101. And I'd say, what's that? You'd say, well, that's an RC circuit. What does it do? Well, it kind of falls off exponentially. And there's a time constant, RC. And here there's a time constant, L over R. Right? So then, I could take my hand off and say, okay, it's an LRC circuit. What does it do? And a reasonable, wild guess would be to say, oh, I don't know. Let me just divide this R into 2 and say it's kind of an LR circuit along with an LC circuit. And the funny part is that's qualitatively correct, provided the system is overdamped. In other words, that the behavior of an LRC circuit, when it's overdamped, is it's a sum of two decaying exponentials. In other words, it's kind of like an LR circuit and an RC circuit. The interesting stuff happens when it's underdamped, and then it's oscillatory, and that's not something. So in other words, then the behavior is qualitatively different from a first order system. Okay, so this is the idea. We can look at a series RLC circuit as well, and you get a different differential equation here. These are, if you go back and look, these are very, very different. And now, to be overdamped requires R large. This makes sense because here there's a current. For a fixed current, the amount of energy you turn into heat depends on R and increases with R. So if R is small, you're back to what you had before. And if R is large, that's large damping. So here it turns out R has to be bigger than 2 squared LC. Oh, I guess there's another observation. I didn't make it before, but I'll make it here, which is that the oscillation frequency, interestingly, is 1 over LC minus this term here. And so that actually tells you that as you turn up damping, the oscillation frequency actually decreases. That's what this says. So that's sort of the idea. And then finally, we can give an energy analysis for these circuits. And that's actually a good way to think about that. So here in either of these two circuits, the magnetic stored energy at any time is 1/2 Li squared, where I is the current through the inductor. The electric stored energy is in fact 1/2 CV squared. Okay? The total stored energy is the sum of the two. That's the total energy stored in magnetic and electric fields. And if you then calculate what the time derivative of the total stored energy is, you just work out what it is. I just take the derivative of this, which is the 2 comes down and kills the half, so I get Li times I prime, plus here CV V prime, and you plug in what I prime is and what V prime is, and you get this. And that simplifies to minus V squared over R. This looks like a silly calculation, but then if you look and understand what it says, you recognize this as something. V squared over R in this circuit is precisely the number of watts that this resistor is dissipating. In other words, the voltage is there. V squared over R is the number of watts. That's the number of joules per second being turned into heat. And so what this equation says is, it says that the time derivative of the total stored energy is equal to minus V squared over R. This is a conservation of energy statement. This is conservation of energy. It says precisely that the time rate of change of the total stored energy is equal to, well, it's the number of joules per second you're removing from the system. That's this, or turning into heat. That's this. Now, what this equation doesn't tell you is it doesn't tell you about the energy which is sloshing around between EL and EC. That's what it doesn't tell you. So, for example, if R is infinity, you get an oscillator, and this is 0. Does that make sense? What does that mean? If the derivative of the total energy in the system is 0, what's it mean about the total energy? It's a constant. Okay? Now, does that mean that EL and EC are constant? No. On the contrary, EL and EC, in fact, are sinusoidal, right? And in fact, in that case, what's really happening is twice per cycle, all the energy is in the inductor or the capacitor. And it's just simply sloshing around. But the sum is absolutely constant. So this is conservation of energy. And you can do the same trick for the series RLC and get the same question. I mean, you pose the same question and you get an answer which is very similar. The form is different. If you think about it, it makes perfect sense because in the parallel RLC circuit, the mechanism of dissipation is voltage across the resistor. This is the mechanism of dissipation. In the series RLC circuit, it's current flowing through the resistor that gives you dissipation, and that makes perfect sense here. Okay. This also explains why it is that critical damping, in the first case, you have to have R bigger than something, and in the second case, underdamping says that R has to be bigger than something, and here it's R less than something. Yeah. Okay. And just to ask you one more, let me just ask one more question. Suppose that this is some giant large circuit, for example, from some giant physics experiment. So I have a very large inductance, a reasonable capacitance, and I have a lot of energy stored in this thing. And I want to choose a resistor to pull the energy out of this LC circuit as fast as I can. Let me hear some suggestions. What resistors would you use? If I make the resistor really large, how fast am I going to suck energy out of this thing? Very slowly, exactly. If I make it really small, some people would say, you know what, though, you should short this. What you should do is you should short this system. That's what you should do. Right? Someone says, I know how to get the energy out of this dangerous thing. Take a crowbar and stick a crowbar across the terminals. So that's someone who advocates using an extremely small value of R. Is that a good idea? You'll get a good spark, that's for sure. But what about, how fast will you extract energy from the circuit and why? If I make R really small, which is dropping a crowbar across this, what happens to the energy stored in the capacitor when I drop a crowbar down? That gets discharged really fast, so I get a really big spark. Congratulations. Now you know what I have? I have a circuit here, which is an LR circuit with a very small r. And what's the time constant? It's L over R, so it's long. So I just kind of, I'm in a bad situation. It's going to take a long time now. Okay? Okay, so in fact, there's an optimal value. What's the optimal value? I mean, what do you think it's going to be? To remove the energy as rapidly as possible from this circuit. It's what? It's critically damped, of course. So you take something in between. And that will give you a solution here which looks like one of these TE to the minus T type solutions. That's what's going to happen. Okay. Now, on the other hand, you could play a couple of other games. For example, if you can hold the crowbar and choose the time when you drop the crowbar down, then you can do pretty well here. What would you do? When would be a really stupid time to drop the crowbar down? When all the energy is in L, and that means that the voltage here is 0. So I could drop the crowbar down, and I've now set myself up for the worst possible thing I could do. What would be the best time to drop a crowbar on here? What's that? Precisely. Yeah. If I do that, actually, I can do really well. Yeah. So, okay. Well, that pretty much finishes up our discussion of second-order circuits, or second-order systems. That's our whole discussion of second-order systems. And let me just recap a little bit what happens here. So second-order system is A y double prime plus by plus y equals 0. Can you go down the pad? There's your second-order system. Now I think afterwards this makes a whole lot of sense. Everything is determined by this polynomial, which is called the characteristic polynomial. You solve this using, of course, nothing more than the quadratic equation, and you get two roots. If you know those roots, you now know, you can say a lot immediately about the nature of the solution here. Immediately. Okay, if the roots are real, positive, negative, if they're imaginary, real part and the imaginary part, they all mean something to you now, I presume, or I hope. So that's the idea. And in fact, it's probably not bad to basically get to internalize the quadratic formula in terms of how it relates to where the roots are. So for example, if I write down s squared plus 10, what's that system? What is it? It's a harmonic oscillator, right? And if I write s squared minus 0.01 s plus 10, yes, anybody here can use the quadratic formula and get the answer. I don't want the quadratic formula. What does that do? About? What do you think? What? Oh, that's underdamped. It's an extreme form of underdamped, right? This is no damping of any kind, right? Let's start with that. This is slightly underdamped. And what is the nature of this? What is this? Please don't, we're only one quadratic formula away from the answer here, but don't do it, right? We're just talking squared, b minus b plus minus squared b squared minus 4ac over 2a. Forget it. Don't do it. What is this? This is the type of thing I'm talking about. You have to internalize what the quadratic formula says. What are the roots of that? Well, b squared minus 4ac. I said don't use the formula. Now here I am using it. Oh well, right? Over 2a. Basically, this is quite negative. So this is lightly damped. It's lightly damped. If this is the characteristic polynomial, the solution is a sinusoid slowly being damped. The oscillation frequency is about square root 10. Okay? Let's do this one for fun. That one. What happens now? It's oscillatory with growth. Okay? With slow growth. Okay. And so on. So I'm just showing you, what number would I pick here to make this critically damped? What would this coefficient be to make this critically damped? That's kind of a nasty question. I don't know. What should it be? I think it's 2 root 10. I think that does the trick there. Am I right? Oh, is that square root of 40? You're right, it is. Fine. There we go. Okay, so that's the idea. So this you don't have to do this because you can always just use the quadratic formula, but it is not bad, in fact, to start noticing things like that. To look at a quadratic and actually just pretty much quickly intuit to have a good intuition for what the roots are going to be. Because what the roots are determines then the qualitative properties of the solution. Okay, I don't think I have anything more to say about that, except that you have a really fun homework problem on your current homework, which is related to this. And I'll make a couple of teasers for that. So far, here's what we've seen. You form this polynomial. And what happens is everything depends on whether or not these roots are real and equal, or imaginary, or complex, right? Everything. The formula changes, and it's kind of clear that at two extremes, these are quite different, right? Something which is a sum of two exponentials doesn't even remotely look like a decaying or growing sinusoid, right? These are just qualitatively different. And that's at the two extremes. Now the question then a nasty question comes up, which is that what happens with a system right around critical damping, right? I can grab, for example, one of these resistors in an RLC circuit. I can make it 10% above critical damping, 10% below, and equal. What happens as we do this? Well, as we change this resistor value, certainly the formula for the solution changes radically, right? It's got cosines and sines in one case, and t, e to the minus t in the other, and two exponentials in the other one. And so the question, which is posed to you on the homework, is, what do you think really happens when you have an RLC circuit and you mess with the resistor and bring it kind of above critical damping, below, and what do you think happens? Any ideas? You think the behavior radically changes? This is a guess. You can't be wrong. I'm just asking you to guess. Who says that as you mess with a resistor around critical damping, you will actually, if I had an apparatus in front of me and as I move through this, something surprising happens? Who thinks something surprising would happen? Okay, we got a couple of takers on that. How about who says like nothing happens, or I don't know, it's just you don't notice anything? Well, what do the rest of you think? Huh? They what? Either or, huh?
Depends on how you define surprising.
Oh, okay, all right. Well, the formula changes radically. Everyone agrees with that, right? Okay, all right. I can see I'm not going to be able to extract anything fun out of you. Okay, let me try another one. Let me take a parallel RLC circuit, or a series RLC circuit. Doesn't matter. And let me consider, now we're going to look at a new value, a new critical value. Here's another critical value of the resistor, whether it's positive or negative. So take a series RLC circuit. Let's take R equals 0, and now I have an oscillator, right? Now make R a little bit positive. And what is the nature of the solution now? So at R equals 0, it's a perfect oscillator. At R very small, what do you get? You get an oscillation which is slowly decaying. And if I make R a little bit negative, a slight negative resistance, what does a series RLC circuit do? What? It's an oscillation, but it's growing. Okay? So there's a case where, I don't know, that's a pretty dramatic change, isn't it? For just a little change in R. That's a hint. Okay, we're going to move on. There's a question?
With changing the resistor value, it's stable at 30 depth, right? So then does that have to do with the linear equation, having to do with the linear equation, where you're
Mhm.
once you move it, it's positive or negative, or it's smaller or larger. It's moving out that stability, so it varies greatly.
Yeah, we can, well, yeah, I don't want to say too much because you have to do the homework problem, but let me repeat the question. The question was, I mean, around critically damped, you're not changing stability, of course, right? Around R equals 0, you are. So you're suggesting that maybe my analogy wasn't great.
Well, no,
No, that's fine. That's fine. That's fine. I'm not going to say anything else. I refuse to say anything else. Yeah, but for the rest of you, please make a guess before you actually find out what the answer is. Please make a guess. Don't. It'll be fun. Right? Okay. Next topic is rational functions and partial fraction expansion. So remember that in theory, I've already shown you how to do an inverse Laplace transform. So you know how to do, in theory, there's a single formula, which is the inverse Laplace transform. As I said before, it's relatively useless because it doesn't really give you any insight for what happens, right? It's just a formula. And a formula is only good for a couple of things, but the one thing you really want is insight, and that one doesn't give it to you. Okay, so now what we're going to do is we're going to look at a method for taking the inverse Laplace transform, which will have the side benefit. Well, truthfully, it'll have the only real benefit here, which is that you'll get a good intuition for it. Right. Oh, yeah, this is probably not a bad time for me to put all of this into context. Okay? Suppose you're doing like real circuit design. I mean, you're actually doing real circuit design. 6 years out, I don't know. You're actually doing something. Do you use Laplace transforms? What do you think? You've designed a circuit. You want to know, does it work or not? What do you think? Don't be horrified by the answer. Okay, we're getting there. What do you think? The answer is, it's kind of, okay, it's complicated. Here's the answer. We can make the answer anything you want. We could say, no, absolutely not. When you design a circuit and you really want to know how does it work, you simulate it. And the simulator is going to, the advantage of that is that instead of a second order system or a third order system or something like that, the simulator is actually simulating a 90th order system. Why? Because computer is just as happy to simulate a 90th order system as a second order system. And all those other orders are things that make the model more accurate. So that when you see the plot come out, there's an exceedingly good chance that when you actually build, when this thing comes back from the fab and you subject it to electrical test, it's going to look very, very much like what you just simulated. Okay? So this would be the extreme point, and you'd say, no, never. No, we don't use Laplace transforms, ever. We just simulate. More accurate, all that. Then you say, but then why did that guy in 102 teach us all this? Right? Any answer? What do you think? Because how did you come up with that good design? All good designs actually start with an understanding of Laplace transforms and all this kind of stuff. So what you do is you have a little amplifier you're building or something like that, and you sit there and you say, well, if I make this transistor too big, this is going to happen. And if I do this, this will happen. You know, in fact, that a reasonably accurate model is 50th order. And you say, well, I'm personally not very good at factoring 50th order, So you say, screw it, we're just going to approximate that as first order, that is first order. And then so you get a rough idea of what it is. Then you look at it and you go, oh, now it's clear. Now it's very clear. If I make this transistor too big, this is going to happen over here. On the other hand, if I make this guy too big, this is going to become severely underdamped, and that's not going to be good. Okay? Then you finish and you say, all right, here's my guess. This is the design, and now you simulate it. So that's, I just thought I'd put it all in perspective. Yeah, so, okay. So in other words, now that wasn't true. I mean, the really interesting part is this wasn't true 25 years ago. 25 years ago, you didn't have these fancy simulators, right? As you really wanted to find out how a circuit worked, you had to fiddle out, had to write out all sorts of Laplace transforms. You had to invert it yourself and plot it. This is it's between you and your slide rule. Okay? This is not true anymore, which is really a wonderful, I mean, it means it means that the only thing that we're really doing here is we're seeking understanding, which is great. especially if you go look in these horrible books which are written on, which is to say all the books. They're still from this mindset of 25 years ago, where it's you and your slide rule and your partial and your inverse Laplace transform table, right? But that's not the point of this anymore. The point is to actually understand, you know, the qualitative nature of these things. Simulators will actually do a whole lot better job of telling you how a proposed design is going to work than anything here. What they won't tell you is if you simulate something and it doesn't work very well, what they won't tell you is how to fix it. And that's what this is for. Okay, so that was I'm allowed a minute or two of that every lecture. That was it. Okay. So what we're going to look at is a method for, which will eventually be a method for inverse Laplace transform, but which has this advantage of having you actually understand how it all works. And so we start with some review. I hope it's review. And so we'll start just quickly reviewing what a polynomial. So a polynomial is a function of this form, right? So it's got a constant term, a linear term, and this is the nth order term. S here is just a dummy variable. I could just as well write W or anything I like. Doesn't make any difference. X. These numbers, A0, A1, which are usually real, but they could be complex, they're referred to as the coefficients of the polynomial. So for example, you might say, what is the S squared coefficient of this polynomial? It would be A2. And assuming the degree of this polynomial is first of all, you toss off all the high order 0 coefficients. I guess it's the largest non-zero coefficient or something like that. It's the number of the largest non-zero coefficient. And we say that a number is a root or a 0, or another name is to say that it solves the polynomial equation A equals 0, if when you plug it in and evaluate it, you get 0. Okay? So for example, the constant 3 is a polynomial. Its degree is, what's the degree of this? 0. It's a degree 0 polynomial. It has no roots. There's no complex number, S, you can plug in such that A of S is equal to 0. Because, well, by definition, every complex number you plug into this polynomial returns the value 3, period. Here's a cubic here. It's got degree 3. And this has 3 roots. 1, you just look at this and you realize very quickly, if you plug in 1, that's a root. If you plug in, what you're left with then after you divide it out is a quadratic, which you can solve, and these are the 3 roots. Okay, and you can check. If you cube either of these two numbers and then subtract 1, you get 1. You get 0. It's a root. Now, if you have a root of a polynomial, then you can factor out that term. So for example, if that's a polynomial, and if lambda is a root, I can divide by s minus lambda, and this is in fact a polynomial. Right? So another way to say that is that if lambda is a root, then A of s is equal to s minus lambda times another polynomial. In fact, the degree of this polynomial is exactly 1 smaller than the degree of A. Okay? So for example, s cubed minus 1 has a root at s equals 1. I can form this ratio of polynomials. Now in general, the ratio of two polynomials is not a polynomial, not even close. Right? So here, however, in this case, when I divide it out, I get a polynomial. I get s squared plus s plus 1. So I get s cubed minus 1 is s minus 1 times s squared plus s plus 1. And this allows us to define the multiplicity. I'm going fast here because this is, I guess review or something like that. So the multiplicity of the root, that's the number of times you can sort of extract that factor, that linear factor from the polynomial. So if I can do this, if I take A of s and I divide by s minus lambda, that's a polynomial. Then I check squared, cubed, and so on. And the largest I get and still get a polynomial is the multiplicity of that root. So here's a cubic polynomial. It has a 0 to s equals minus 1. I divide by s plus 1, and I get s squared minus 1. This still has a root at s equals minus 1. So I divide it again. This does not have a root at s equals minus 1. So that you'd say that the multiplicity of the 0 at s equals minus 1 is 2. Now the reason we're telling you about the multiplicity is not only is it going to have a big effect on various qualitative dynamics later, but it's important here because we need to account for we have to do our accounting correctly when I ask you about the number of roots of a polynomial. And the reason is something I guess I don't know, I'm sure you've all seen, is this fundamental theorem of algebra that says that if you have a polynomial of degree n, it has exactly n roots. But you have to do your accounting just right, which is to say you have to count s minus 1 cubed, for example, as 3 roots at s equals 1. That's what you have to do. Now what this says is that you can factor a polynomial. So if I can write it out. This is sort of the coefficient data structure, and this is the root or factored data structure for a polynomial. Okay, that's how it works. And these are the roots. So this is actually it's an interesting relation between these two data structures. Okay, so for example, if I gave you an and the roots and asked you to convert to this coefficient data structure, is it easy or hard? How would you do it? I give you the lambdas and I give you the ans. How would you convert to this data structure? Could you do it? You just multiply it all out and collect the terms. It would not be fun, right? Because when you multiply this out, you're going to have 2 to the n terms. So if it's a 10th order polynomial, right, then you have 1,000 terms. Okay, but in principle, you could do this. Okay, how about the other way around? What if I give you the coefficient, this data structure, and I ask you to go to the roots? What do you have to do? Yeah, you have to factor it. You have to factor the polynomial. You have to find roots. And actually, here I'll tell you what we'll do in the last 1 minute. I'll tell you a little bit about factoring polynomials. This is fun, and then we'll have our quiz. So actually, you thought I forgot about it, right? Actually, you know how not? It's because the attendance doubles, so I'll never forget. Although one class once they actually they got me to. They almost pulled it off. You know how they did it? It was pretty good. Right as we're coming up to it, we got to something really interesting, and they started asking this really interesting question. I said, "That's an excellent question." We talked about it for a few minutes, and then they just kept going on and on. And then I looked down. And I said, "I know what you're doing." And they actually, I mean, they didn't even deny it. They didn't deny it. They just, yeah. Anyway, it didn't work. All right, so I'll say a little bit about factoring polynomials, and then we're going to have our quiz. Even though factoring polynomials is really interesting. Okay, here's the deal with factoring polynomials. Is it easy or hard to factor a degree 1 polynomial? That's really quite easy. How about quadratic? Okay, that's high school. Cubic? What do you think? Yeah, well, let's say it used to be. Okay, so the deal with, I don't know, how many people here actually does anyone here actually know the formula for the roots of a cubic? No, good, okay. However, there is one, and it is not minus b plus minus squared b squared over, whatever it is, okay? That's fine. It's half a page, formula for a cubic. It's not attractive, but it exists, okay? Quartic. Okay, so quartic. Well, turns out, okay, also, how many years has this been known? Quadratic, couple of millennia, okay? Cubic, somewhere in the 1700s, okay? Quartic, 80 years later, after like all the best mathematicians worked on it, it popped out, quartic. And let me say this, it is not attractive, okay? It's like 2 pages. And in fact, it's only 2 pages because you start by defining various things, and then you come back and you have more formulas involving those things you just defined. It's not attractive. That's the quartic. And that brings us to the 5th order one. And this was this burning mathematical question. All the best mathematicians worked on the formula for the roots of a 5th order polynomial. No one was expecting it to look good, because after all, look at the trend. For an order degree 1 term, it's trivial. Degree 2, it was known for millennia. Degree 3, half a page. Degree 4, 2 pages and not attractive. You can see the trend. And I'll tell you what do you think was the end of the story? What? Very famous fact. What? It turned out, after all these mathematicians killed themselves, a couple of them actually came up with alleged formulas, and they had special cases knocked off and all that. Then some kid, about 22 years old, actually proved there is none. Can't be done, period. Impossible. There is no formula, which is just as well because, anyway, for us it's okay. This irritated people for a long time. For us it's perfectly okay because we have computers. And how hard is it, in fact, for us to factor, say, 100-degree polynomials? How long does it take? Like me, for example. Well, me in my office, let's say. There's your hint. There's your hint. Yeah, a whole lot faster than I can type it in. It's in the millisecond range, right? So, but anyway, it's a famous result. Fifth-order polynomial, no formula. Okay. Ah, you're trying it. His name was. All right. Good try. You have 4 more. I'll tell you his name. His name is Galois.